6a. We're told that the half-life of carbon-14 is 5,715 years, and we are asked what percent of a given sample will remain after 1,200 years. So this is an example of exponential decay, and it uses the same formula as the exponential growth problem. So it's using the exponential growth model. It's just that the population will be decreasing rather than increasing. So we'll still use this same formula. Y equals c e to the kt power, and then c and k are constants that we'll have to determine. Alright, as with exponential growth, c is the initial population, in this case the initial amount. Well, we don't know what the initial amount is. We're not given the mass. So what we can do, especially since we're asked about percentage, is let's just assume that the initial population or the initial amount is 100%. So when t equals 0, the amount of carbon-14 in our sample is 100%. I think I won't bother to write the percent. That might be confusing. I'll just write 100, and then I'll note here that we do mean it to be percent. Now the half-life is 5,715 years. So what that means is that after 5,715 years, the amount that remains will be exactly half of what we started with. So that would be 50%. Alright, so let's go over here. We'll put in the 100 for C. And now we need to solve for K. Well, that's where this information comes in, the half-life. So after 5,715 years, the amount of carbon-14 will be only half as much. It will be 50%. So we'll put 50 in for Y. T is 5,715. And we solve for K. So let's divide each side by 100, and we get 1/2 equals e to the k times 5,715. Next we need to get rid of the e, so we take the natural log of each side. Those go away, and we're left with 5,715 K. Now we divide each side by the half-life, 5,715, and we get K. So I'm getting K to be the natural log of 1/2 divided by 5,715. Now I will put that into my calculator and see what I get. So the answer I get, let's see, my calculator tells me it's about negative 1.21, I think I'll call that 3, e minus 4. This, of course, is my calculator's way of doing exponential notation. So what I need to do is just move the decimal point 4 places. Since this is a negative number, I'll move it to the left 4 places. So 1, 2, 3, 4. I'm going to have to put in some zeros. I think that will be enough. The decimal point was originally here. Move it 4 places to the left. 1, 2, 3, 4. That'll work. And so I'm getting K to be negative 0.000123. So that means that the exponential decay model, or radioactive decay model, whatever you want to call it, is going to be y equals 100 e to the negative 0.000113 t. We found c, and then we found k. At this stage, we should be able to find the answer to the question we're asked. What percent will remain after 1200 years? So that's where we need to substitute in 1200 for t. So we'll have negative 0.000113 times 1200. And so be sure to, when you calculate this with your calculator, be sure to put the entire exponent in parentheses, or you may not get the right answer. Alright, so I am now putting everything into my calculator. And I am getting, looks to be about 86.45. Of course, that'll be percent. Now, if yours is off a little bit, that's okay. I think my answer, the answer I have in the solutions is maybe 86.46. These are approximations. So if you're off a little bit like that, it's okay. 8b, we are asked how long it will take for 1/10 of this sample of carbon-14 to decay. So I've got the model, the exponential decay model that we have developed already. And let's see, we need to answer the question. All right, so what's going on here is we want to know how long it would take for the sample to lose 10%. You've got to be a little bit careful here, because this y is not how much has been lost. Y is how much remains. So if 10% decays, if 10% is lost, that means 90% remains. So that's what we're going to put in for y, 90%, or just 90. You'll remember that we're measuring the amount as a percentage. The initial percentage is 100%. All right, so I put in 90 for y. Now divide both sides by 100, and we get 0.9 equals e to the negative 0.000113 t. And we next, let's see, we're trying to solve for t because we want to know how long this will take. So we need to get rid of the e. We'll take the natural log of each side. And now the right side simplifies because the natural log of the e and that formation cancel each other out. So we get the natural log of 0.9 is equal to negative 0.0001213t. Divide each side by negative 0.0001213, and we're done. So now I'm going to enter this into my calculator. And I am getting let's see, about 868.6 years. Time is measured in years now. And let's see, in my solutions, I've got 868.7 years. That's close enough. I may have rounded differently when I was working on the solutions before.